Hello, in this video we're going to look at the intersection and union over an indexed family of sets. So let us begin with an open interval defined as follows. Let a sub n be equal to the open interval from -1 over n to 1 over n, where it's implied or assumed that n is a natural number. So let's begin looking at what these intervals look like. For example, when n equals 1, our open interval looks like the open interval from -1 all the way up through 1. And keep in mind we have all the numbers in between as well. So these are all the x values that are strictly greater than -1 and strictly less than 1. And for a sub 2, if we plug a 2 into our formula here, we'll get a -1/2 up to 1/2. And again, it's open intervals, so we'll include the open dots on those endpoints and all the numbers in between. And we could keep going. I'll do one more and then we'll use our imagination to think about what it would look like if we kept going. So we'll go -1/3 to 1/3, again open endpoints and all the numbers in between. And eventually my pen gets too clumsy of a tool to keep writing these, so we'll just use our imagination for what would happen if we kept taking n to be larger and larger. These little intervals would become smaller and smaller, but we would always have something in there. In fact, if we plot the point 0, we notice that 0 would be in every single interval, no matter how big our n gets. So the intersection of these, if we do the intersection, this is simply the intersection A1 intersect A2 intersect A3 dot dot dot. So we're going to do an infinite intersection here. And as we said, the only point that's going to be in all of those is 0. So this would be equal to the set containing 0. It would be a singleton set, so we've got curly brackets around that 0. Now for the union, we're thinking about the union A1, union A2, union A3, dot dot dot. It's an infinite union, so we're doing the union of all of these, and really the union is just going to be our original A1, the open interval -1 to 1. Let's do another example. Okay, so for our second example, let's let b sub n be the half open interval beginning at 3 and ending at 3 plus 1 over n. So if we draw out a few of these sets, and then we'll use our imagination to think about what happens if we kept going. But B1, let's see, B1 would be a half open interval, so we're starting at 3 and we go up to 3 plus 1 over 1, which is 4, so we'll end at 4. It's closed on 3, open on 4, and all the points in between. So for example, this would be the interval 3 is less than or equal to x is strictly less than 4. Okay, let's look at B2. B2 again starts at the 3, closed on the 3, and this time it only goes up to 3 plus 1/2, so that would be 7/2 or 3.5, somewhere about here. And all the numbers in between. And for our B3, we've got closed on the 3, and we're going to go all the way up to 3 plus 1/3, which is 10/3 or 3.3 repeating. And open on that right hand endpoint and all the numbers in between. And we could keep going. So let's look at what the intersection would be as n goes from 1 to infinity of the b sub n's. Well, this is simply b1 intersect b2 intersect b3, etc. And so if we look at the intersection of all of these, we're looking for points that would be in every single interval, no matter how tiny those intervals get. So that right-hand endpoint is moving in closer and closer to 3. It never gets to 3. Right? That right-hand endpoint is always 3 plus a little bit more. So we're assured that 3 is always going to be in this interval. And in fact, that's the only thing that's in this interval. So again, we have a singleton set. It's a set containing just the number 3. The union, as n equals 1 to infinity, of our b sub n's would look like the union of b1, union b2, union b3, etc. And the union of these, well, that's just going to be our original set that we started plotting, our b1, and that's because we're looking for the set of points that are in b1 or b2 or b3, and because b3 is a subset of b2 and b2 is a subset of b1, it's just going to be our original set. Okay, let's do one last example. In this example, we're not going to look at a number line. We're not going to look at the real numbers, but we're going to look at actually a discrete set. So we're not looking at intervals of the real numbers. We're going to look at a discrete set. And the discrete set has the numbers 1, 2, 3, all the way up through n. So let's plot out a few of these. When n is 1, we just have a set containing 1. When n is 2, we have the set containing 1, 2. When n is 3, we've got the set containing 1, 2, 3. And we get the idea. We could do the nth set, which is a set containing 1, 2, 3, n, and we could, go out to 100 if we wanted to. But at this point, we're kind of getting carried away. Okay, and we could keep going. We could let that n get as big as we wanted to. N's a natural number, so that could actually be an infinite list of sets. So again, let's look at the intersection as n goes from 1 to infinity of the c sub n's, and also let's look at the union as n goes from 1 to infinity of the c sub n's. So for our intersection, we're looking for elements that are in C1 and C2 and C3. We're looking for elements that are in common to all of these infinite sets. And the only element that's in all of the sets is 1. For the union, well, let's see, we're looking for elements that are in C1 or C2 or C3 or C sub n or C sub 100 or as big as we get. And what we notice when we let these sets, when we keep writing them out and we keep going with this process, if we did this from n equals 1 to infinity, we would get all natural numbers. And some books define the natural numbers to start at 0, and other books start the natural numbers at 1. So you might want to even be more explicit here and say these are going to be the positive integers. That would avoid any confusion. Another way to avoid confusion would be just to list 1, 2, 3, ... and then it's clear that you mean the set starting at 1 and going off to infinity.